Hello and welcome to today's webinar, Statistical Power from First Principles, Approximate, Exact and Simulation Approaches to Calculating Power. Today's webinar will provide you an overview of what statistical power is, how it interacts with the hypothesis testing framework, how it can be used in the context of clinical trial planning, and the practical approaches available for calculating statistical power in your clinical trial. Before we get any further, just some frequently asked questions. Firstly, is this webinar being recorded? Yes, and the recording and slides will be sent to you after this webinar is complete. You can also find them on our website, statsols.com, alongside the recording and web slides from all previous webinars in our webinar series, which is run each month. If you have questions, please use the questions option within the webinar window. It should be a question mark within a speech bubble. If there's time, I'll answer some of these questions live. Otherwise, I'll answer all questions asked via email after the webinar is complete, either later today or tomorrow. So once again, thank you so much for coming to today's webinar, Statistical Power from First Principles, presented by Dominic Enquiry. As I mentioned, the hope here is to provide you kind of a breakdown of what statistical power is from its most basic level, how it then interacts with the hypothesis testing framework and some of the debate about that there, and then how it's more practically used in the context of clinical trial planning and sample size determination, and then these three main approaches to calculating statistical power: the analytic or approximate approaches, the exact approaches, and then also the simulation-based approaches. This webinar is a bit more technical, a bit more statistical than our usual webinars, so that may be an issue for some of you. But if you're more interested in the kind of more practical aspects of sample size determination and clinical trial planning, there was a webinar run last year, Everything You Need to Know About Sample Size Determination, which gives a much more practical view on this aspect of clinical trial planning and power calculations and sample size determination. So that may be a bit more interesting. As I said, that's available on our website alongside our all other webinars at statsols.com. However, if you're interested in this journey of talking about statistical power, let's go ahead. So my name's Ronan Fitzpatrick. I'm the head of statistics here at Enquiry, and I'm very happy to have all of you here today. In terms of what we're going to cover, we're going to first cover what statistical power is at its highest level, and then break that down into how it looks within the hypothesis testing framework. We'll then talk about power in the context of clinical trial planning, and then these practical approaches to calculating power, these analytic approximate approaches, these exact approaches, and these simulation-based approaches. At the end, there'll be some conclusions and discussion. As mentioned before, today's webinar is brought to you by Enquiry, the complete solution for optimizing your clinical trial designs, from preclinical research to confirmatory trials, covering sample size calculations, power calculations, adaptive design, randomization lists, and much more. And you can see here a flavor of what's available in the software at present. We're always adding additional features, so if you're interested in something that's not available here, you can go to the website to check that it's not there. But if it isn't, please do get in touch. That kind of feedback is very valuable for deciding what we work on in upcoming updates. Note that Enquiry is a licensed product which has tiers, and effectively our base tier relates to our standard power and sample size calculations, plus is related to our Bayesian sample size features, Pro is related to our adaptive design features, and Expert is focused on our simulation tool specifically for milestone prediction. There's a URL on this slide if you want to know more and see a full breakdown of what's in each of these tiers at present. So let's firstly get into statistical power and what it actually means. So I think what I'm actually going to do provide first is kind of the highest level, almost the step zero for understanding statistical power, because usually if you like read a primer or another paper on this, they'll usually talk about in the context of hypothesis testing, which we'll get onto in a moment. But I would like to make the argument that statistical power is a much wider concept and that is applicable to any scenario where you're willing to make a few fairly, standard assumptions. Firstly, you're basically willing to make an assumption about what statistical procedure you're going to use and what a given outcome is going to be. So the outcome could be what includes things like our study design, but also what would a success mean? Like what is a scenario in which we would consider our trial to have succeeded, like a mean difference of 1 or a hazard ratio of 0.5 or something like that. So we're willing to define a scenario, both in terms of the design, but also like a specific situation, like a specific set of data occurs. Like if we want basically say, what's the chance that given that scenario occurs and we're going to apply a statistical procedure to get some kind of criterion out of it, that we would find for success? That is for me at a highest level what statistical power is. So like in the concept of hypothesis testing, in practice that means we assume an effect size and then we say like if the p-value is going to be below our test significance level threshold, we're going to find for success, we're going to reject the null hypothesis, and that's going to be power related to that. but it could be, applied to a much wider set of scenarios than that in reality. So as long as you're willing to say that statistical procedure is going to provide an output or outputs that are congruent with concluding for success, for finding in favor of conclusion, and I mean that just at the broadest sense, not a statistical sense, but just purely like this means we would, find for success, or we take it to the next step, or we take it to the FDA, or whatever that happens to be. That is a scenario where you can calculate, in theory, a type of statistical power. And as I said, there are other scenarios, other types of statistics that are used out there that are alternatives to p-value in the context of hypothesis testing. So the Bayes factor, which is maybe more of a kind of hybrid approach, an extension of the p-value from certain perspectives, or you can calculate the lower bound based anyway. If the Bayes factor is your criterion for success, if you're willing to define a critical threshold for the Bayes factor of say 10 or 20 or 30, so if the Bayes factor is above that, and we're willing to predefine some specific scenario for our data pre-trial, that can be used as the basis of our power calculation. And indeed, there are a couple of tables of inquiry for calculating sample size for the two means and one means case using Bayes factors. But even in the context of, say, interval-based sample size. So usually we think about interval-based sample size. We want the width of our interval to be a certain size. So let's say from a width of 1, whether that be the full width or the half width, it depends on your perspective. But effectively, we have a width, a precision for our estimate based on the interval, and that's our target. And usually we just do a calculation, and effectively that calculation comes out to basically say, on average, we want the width to be around what we specified. But you can add in, basically some additional calculations, what we call a tolerance probability, or it's given some other names in different probability success criterion and other sources. But in effect, you can specify, the probability that your width will be lower than your specified width. So if you want to say, the width is 1, but I want to be 80% chance that the width will actually be less than 1, then that 80% is effectively equivalent to statistical power. So you can see that even if we go into Bayesian criteria or into interval-based success or criteria for how we're going to define what's going to happen in a trial, power can still be extended to those in some way. And so I just want to give that kind of step zero to what statistical power is before we get into this more traditional approach of talking about in the context of statistical hypothesis testing. And what I want to say is that power, it's a vital concept for planning, for comparing methods and finding the sample size, but it does have a very useful utility within the context of statistical theory as well, which won't be a focus today, but it is something that is very useful to know about. So as I said, this webinar, we're going to talk about what power is, mostly in the context of hypothesis testing. We're going to talk about how it's used in sample size planning and clinical trial planning generally, and then talk about these three main approaches to calculating power once you're actually getting down into a real trial. So we can't really talk about power in its more traditional sense without talking about hypothesis testing. So null hypothesis significance testing, or NHST, is by far the most widely used paradigm for statistical testing, for hypothesis testing in clinical research. Whether it should be or not, that's a very wide debate. There's lots of debate about this. There's the p-value statement from the ASA several years ago on this. There's the Bayesian perspective. There's different frequentist perspectives, such as like severe testing from Deborah Mayo. So there's a whole wide range of different views on what hypothesis testing should even be. But in practice, we have what we call this NHST framework, and it is still by far the most widely used in real clinical research, in real clinical trials. Well, there's a whole debate about whether it should be, but that is the reality of where most research is at the moment. And NHST, in terms of the history of it, it's basically a compromise between what we're kind of traditionally called the Fisherian approach to hypothesis testing and the Neyman Pearson version of hypothesis testing, with Fisherian approach basically being very solidly focused on the null hypothesis and the p-value, and effectively you have a null hypothesis and the p-value is representative of how likely that null hypothesis is in some interpretation. I'll get into the more exact interpretation in a moment. And therefore, given some null hypothesis, how likely are we to be in that world is basically what the p-value represents. And the Neyman Pearson was much more of a test view and have brought in the type 2 error and stuff like that. And it was much more focused in like a repeated experiments and creating a framework for doing that and finding tests which are likely to find for the type 2 for the conclusion, while controlling strongly the type 1 error. So the actual reality of Fisher and Neyman and Pearson and the relationship between them, and what they actually did in practice, that Fisher used thresholds and occasionally talked about power. Neyman Pearson used p-values, didn't just talk about alpha errors and type 1 and type 2 errors in practice. So it's much more complicated than the potted history we give you, and there's some really good references at the end of this slide deck from Lehman in particular, who was mostly under Neyman Pearson in his education, which goes into much more detail. But in practice, we have this kind of compromise called NHST, which is mostly focused on basically taking a p-value and comparing it to a threshold, a test significance level. We call that in the context of inquiry. And so in this NHSC framework, our primary thing we're trying to do is decide whether or not to reject the null hypothesis. So basically, we're going to reject the null hypothesis and say our data is not compatible with the null hypothesis, or we're going to fail to reject the null hypothesis. And we're going to basically come to the conclusion that we can't say this is not compatible with the null hypothesis. And that's, just to be clear, it's not the same thing as saying it is compatible with the null hypothesis. That would be much more a kind of an equivalence hypothesis if you're talking about, say, a mean difference of 0. So there's a whole wide set of kind of technical things you need to keep in mind. But basically, you're either going to reject the null hypothesis or you're going to fail to reject. You never accept the null hypothesis. That's a different type of test, effectively closer to equivalence testing if you're interested in that view. And as I said, the most common null hypothesis is basically we're talking about superiority or inequality. Now, technically, that's actually the alternative hypothesis, that we have superiority or it is unequal, but the null hypothesis is obviously just the inverse of it. It's for equality, it's for non-superiority, for lack of a better term. But there are other types of hypothesis sets out there, and these were covered by my colleague Dennis Desmond a few months ago. As I said, all of our webinar series is on our website, statsalts.com, and that covered non-inferiority hypotheses, super superiority, and equivalence. Super superiority, also known as superiority by margin in some contexts. And these are basically more complex hypotheses than the kind of classic superiority inequality hypothesis. So in practice, what is our null hypothesis? How are we actually going to use this null hypothesis? So we define a null hypothesis. So for example, we can see here that the mean difference is less than or greater than 0, and the alternative being that the entire rest of the space, which is greater than 0. And just note that this could be equal to 0 and then not equal to 0. It doesn't make a huge difference, except effectively your alpha is halved, and you kind of have to worry about the lower tail to some extent for power calculations. But in practice, this one-sided hypothesis at 0.05 is equivalent to just a two-sided level would be equivalent to 0.65 at the one-sided level. So basically, we have our null hypothesis. Then we're okay. Well, what is our success criterion going to be? Like in practice, what is the thing we're going to use as deciding whether to reject this null hypothesis or not? And that's basically going to be based on this criterion of the type 1 error. So basically, that is like the probability of rejecting the null hypothesis, H0, when H0 is true. And that is basically our type 1 error, or our false positive error, or our alpha error, and a whole bunch of other interpretations basically that you can give there. But we'll talk about that, basically the type 1 error. And when I say true, the null hypothesis true, really that's a simplification. It's really the type 1 error, the null hypothesis being true, and all the other assumptions that we made into doing our model being true, so that we're going to use a t-test, and that we have independent samples and IAD assumption, and 2 independent groups, and all these other assumptions that went into our model. It's really being, like you could argue that, to some extent, hypothesis testing is saying, assume you're wrong. How likely is it, given that what occurred would happen, given that you're wrong? But it's more like being very specifically wrong. Or there are certain approaches to hypothesis testing that are a bit more flexible, but in practical terms, assume that you're wrong in this specific way. How likely is it that the data that did occur would happen, given that wrong scenario, that null hypothesis, is actually true alongside all of our other assumptions? So in practice, what are we actually doing? Well, effectively, we're going to reject the null hypothesis. We're going to find for quote unquote success. It's controversial to say that for some statisticians, but in effect, if our p-value is quote unquote significant, we're going to basically take a p-value, which is our estimate of the type 1 error, and then we're going to see if that's less than our decision boundary alpha, which is basically our test significance level alpha. So I'm using alpha twice here, and basically the Fisherian and Neyman Pearson stuff is where those kind of conflicting interpretations kind of come into a lot of context. But in practice, basically you have your estimate of alpha, the p-value, and we're basically going to see, is that lower than the desired overall type 1 error rate for our test. But so like that's really mixing the two interpretations up. But in practice, we usually talk about p-values in the Fisherian ways, but they're used in the Neyman Pearson ways, probably the way I put it. So Neyman Pearson testing, where it's talking about repeated testing or repeated sampling, that is basically, you're setting an alpha, and then we're saying that basically if we run this test 100 times, 1,000 times, under the null hypothesis, we'll get 5% of those will end up happening to reject the null hypothesis. And that's the Neyman Pearson approach. The sharing approach is like get a p-value and then kind of use that as a decision criterion for how much we think the null hypothesis is unlikely to be true, and basically create a success criterion based on that. So just like they're kind of somewhat incompatible, but that's basically how they were stuck together in the NHSC framework. Whether they should have been or whether that's the correct approach is a whole other debate, which I won't get into, but it's a very interesting area if you want to know more about it. So if we go back to our here on the right, you can basically see that for, say, a two-sample z-test, we have our z-statistic, which is basically our mean difference, x dash 1 minus x dash 2, divided by our standard error, which is just, the variance divided by n in each group. In this case, I've made the simplifying assumption that the standard deviation is equal in each group, s is equal in each group, and n is equal in each group. So n is the sample size per group here, just to be clear here. And under the null hypothesis, this is obviously a standardized z-statistic. Basically we're assuming that, under the hypothesis, the mean difference is 0 under superiority. So this z-statistic will have a distribution that is normal with a 0, 1. So a standard normal distribution by all accounts. But I will briefly mention that, okay, you can think about that in practice. What does that mean in reality? Basically, we can then define, given our alpha, or 1 minus the alpha, if you want to make the z-statistic positive, we can basically calculate that for the z-distribution using, something like QNorm in the OR programming language, or similar in like Excel or SAS or whatever. And basically, we want to convert, our alpha into the critical z-statistic. And basically, this is z-statistic above which, if our actual z-statistic in the study is above that, we're basically going to say, actually, that z-statistic is not compatible with null hypothesis and all other assumptions, and therefore we're going to reject the null hypothesis. And so in practice, basically, you take your alpha of, say, 0.025, turn that into a z-statistic of critical z-statistic of 1.96, and then basically you say, if our z-statistic is greater than that critical z-statistic of 1.96, we're going to reject null hypothesis. That means that if under the null hypothesis, where the actual mean difference or the effect size is 0 in this case, if we're talking about difference scale, then if that happens under the null hypothesis, where the actual mean difference is actually 0, so we're assuming the mean difference is actually equal to 0, given that's actually true, we don't want that probability to be greater than 0.05. So we don't want more than 5% of the time or 0.025% of the time to be higher, to make that mistake, basically that type 1 error. I also do show that, if we extend this to other types of hypotheses, the only real difference is that for non-superiority, supersuperiority, we basically replace 0 with some kind of other specified value, let's say minus 0.1. And for equivalence, we're now testing, are we between two boundaries, the lower and upper equivalence boundary, rather than, just testing against the kind of point hypothesis. So it's kind of a bounded hypothesis effectively. So all that begs the question, like statistical analysis, to do it like a test in SAS or SPSS or GraphPad or another statistical software, all you need to do is define your null hypothesis. All you need to define is your alpha. So why are we even worrying about this alternative hypothesis stuff? And that's where statistical power comes in, or that's one of the reasons why worry about statistical power. So the probability of not rejecting null hypothesis, basically, failing, quote unquote, when the alternative hypothesis is true, is our type 2 error. So that's our false positive error. So just imagine a scenario. Now we're going to assume not that the null hypothesis is true, but that some alternative hypothesis is true. So let's say the effect size of mean difference is equal to 1 with some given variance. So now let's assume that's true and actually say clinically relevant. It's actually something that would be good to happen in our actual study. Given that's true, the alternative hypothesis is true, how likely is it that our procedure will still fail to reject the null hypothesis? So we'll get a p-value that's above our critical test significance level threshold. And that basically is our type 2 error, our beta error, our false positive error. And so power is actually then just equal to 1 minus that probability, that false positive probability, that beta error. And in that case, effectively, if we make the switch, this is what happens in null hypothesis that z is greater than z alpha, the critical z statistic. Basically, if you replace h0 with h1, that is effectively our power. That we reject the null hypothesis, that we have a quote unquote success. If that happens under the null hypothesis where it shouldn't be successful, that's bad, that's an alpha error. But if that happens under the alternative hypothesis where we actually do have an effective interest, that's good, and that's our power. And that's basically where these two parameters come in. And you can kind of see here on the right a derivation of the power for that two-sample z-test scenario. And this derivation is relatively simple. In most cases, this will be a bit more complex. But in effect, we have our z-statistic as before. I've made a little reformulation here where effectively I've brought an n minus 2 square root over here. That'll make sense when I get further down. But you can see this formula here. You can see here that this is going to be our standardized effect size under the alternative. It's going to be equal to the true effect size, so the true mean difference that we don't obviously know, but we'll assume that's the true mean difference divided by the true standard deviation. So that'll be sigma here rather than s, which would be our sample standard deviation. And basically we're going to say that power is how likely is this z-statistic to be greater than the critical z-statistic? So remember, the power isn't affecting the critical z-statistic. We're still using the same decision criterion as defined from the null hypothesis and the desired alpha rate, but now we're given h1 delta is equal to delta 1, that we actually have this effect size of interest. And basically, if we look at this inequality here, if we were to subtract the same term from both of these, we can see that by definition, if we subtract this effect size, so see this delta here, we're now multiplying this by n minus 2. So you can see that that's basically the same thing we're doing up here. And so effectively, this ends up, if you subtract this from this, creating a mean difference of 0, and that then therefore happens to have a standardized normal distribution of 0, 1. Which is the definition of a standard normal, to be fair. And so you can see here that effectively this is saying that x, which is standard normal 0, 1, is greater than this term here on the right. That is going to be equal to our power. And if you know your statistical theory, that's effectively just equivalent to just saying, okay, apply, p norm here, basically the inverse, the cumulative distribution function of this here, or the inverse, I should say, and that basically gives you something that looks like this. So you can see here that this term becomes x, and then basically you run the standard normal distribution, p norm, if you're looking at OR language, and that is run on this term here on the right, and that basically becomes our power. And then if we rearrange that, we can get this out here, such that this formulation here would give us our statistical power. And oftentimes you will then see this rearranged for n to give you this here. And if we return this delta term back to its original meaning here with the mean difference and standard deviation, that gives you this equation here, which you'll see very commonly used for the sample size for the 2 sample z-test and the 2 sample t-test as an approximation for the latter. So look, obviously this isn't a maths webinar. Obviously, so I'm not going to go into much more detail in that, but if you want a derivation, that's a very quick derivation there. I'm happy to go into more detail if you're interested later on. And so the one thing I just would emphasize once again is we're making here a specific alternative. So we're not just saying, here generically the alternative is greater than 0, this entire space. We're now making a claim that under some specific alternative, which is something that isn't required to do the test, we don't need to, well, at least unless we're going to the Neyman Pearson approach, which obviously is practically not what NHC does. But in practical terms, in most people who aren't using the Neyman Pearson approach, we don't need to worry about the H1 value. We don't need to worry about what the specific alternative is. Except we're talking about the statistical theory of like uniformly most powerful tests and stuff like that, Pearson lemmas. But in effect, we're specifically saying, the effect size is 1, or the mean difference is 1, or the hazard ratio is 0.5. So we're making that specific assumption. Really, it's that value or higher, or like more extreme. But like we'll just say it's the value you specify as kind of the lower bound, or the kind of critical value, the critical alternative value. And that's basically what we're going to use into our power calculation, and to calculate this type 2 error, and then calculating by extension our power. And as I said, that value might be your expected value or your clinically relevant value. And I suppose the important thing to note there is that there's a whole wide variety of different opinions about how you should pick that effect size for your power calculations in a real clinical trial. There was a webinar by my colleague Calvin O'Brien, which covered that in a lot more detail if you're interested in knowing more about that. So what is H1 adding? Well, basically it adds a lot on the theory side if you're going to go into the Neyman Pearson side and uniformly powered most powerful tests. But in practice, what it's really valuable for is allowing us to evaluate the chance of our trial succeeding, given our willingness to create a hypothetical scenario in terms of what we're going to do, in terms of our statistical test, our design, our success criterion, and then all the other choices we could make. And then, as I said, one choice, which is usually free, which is how big do we want our study to be? So when we talk about power in the context of clinical trial planning, power is this really useful metric for planning a trial. Now, post hoc power does exist. You can calculate power, based on what actually happened in your trial. But I would argue, and many other authors have argued, that it's not that useful, especially the way it's usually done, which is you kind of take the mean difference you actually got in the study and the variance you actually got in the study. You input that into your power formula, and you kind of say that was the power of the study. You can easily show that the power is, in that case, just a reformulation of the p-value. So if the p-value was non-significant, or failed to reject the null hypothesis, then that is going to give you like a low power. That's just the way it is. Those things are just directly related to each other. So in that sense, it's not adding anything above the fact you've got a p-value. I think the problem is that in practice, people would, get a non-significant p-value. They would fail to reject the null hypothesis. They would then do a power value. So, well, we had low power all along, but that's not really what you had there. If you powered for a pre-specified effect size, you were powered for that effect size. The fact that the effect size came out lower, that is just what happened in the trial. The power had nothing to do with that per se. So I would really say power is mostly for planning trials, not evaluating trials or evaluating data. So I think just before we get to the sample size aspect, it is important to note that power can be very useful for evaluating between the different choices you have at the planning stage. So what design you want to use, what statistical method you want to use, you want to include covariates and all these other choices. So, like these are all things that can be very useful for understanding your trial and how feasible it is really. Like if your effect size mean difference is going to be 1 with a variance of 2.5, is that going to work for a t-test with the number of samples you have available? So it can be very useful in that context, although it's often misused because people just kind of move what's really not a free variable, which is like the effect size, which you really should be based on something either clinically meaningful or what you actually expect to happen. But in practice, people just move that around, and that's kind of what we call sample size theater. Such as authors like Darren Daly would argue it's very bad. Now it's covered a lot more in the webinar I referenced previously about everything you need to know about sample size. But basically, in power calculations, we have all of these things which are either fixed or estimated. So, the study design, the statistical method, the hypothesis test, the significance level, these are all things that we usually are fixed a priori at the planning stage. And then there's things we need to estimate, like the effect size or nuisance parameters, like the variance. And these aren't things that we can really change, right? These are things that are either defined by the regulator or by our sponsor, or which are based on estimates, like what we think is actually going to happen. We obviously can't just change that arbitrarily to kind of make the power calculation work, or at least we shouldn't. And so the thing that's left over, that's free, if we say go back to the derivation here, is the sample size. So we can increase or decrease the sample size freely, obviously not free in the financial and logistical sense, but in the sense of these kind of hypothetical calculations, that's the thing that we can do. And so basically, as we increase the sample size, we will increase the power, because basically the standard error will come down if we talk about that z-statistic example. But overall, that's basically true if you get down to it. For most cases, we're going to have more accurate estimates as sample size increases, and therefore we'll have higher power for that specified alternative. So, if we've specified the alternative hypothesis is true, then, the more precise our estimate is, the more of our distribution will basically be in the rejection area, and less of it will be now still stuck in the null hypothesis area. And so in practice, if we're doing a clinical trial, usually what we're going to do is we're going to keep increasing sample size until we reach some critically desired power, which would usually be either 80% or 90%. 90% would be the more common one in clinical trials at phase 3 due to the 2 trial rule, but 80% is also widely used as well. And so this slide here just provides kind of a brief overview of these kind of things that you could do to increase the power. So one thing is you could be more liberal with your alpha. So you could increase alpha from 0.05 to 0.1. That's something that you might be allowed to do. And obviously there's a whole other debate about the appropriate way to pick the p-value and its actual interpretation. And there's a good paper by Nuzo that talks about p-value doesn't really mean what you think it means and stuff like that. But a lot of these references are included at the end of the slide. But in effect, that's one thing you could do, right? And that's effectively equivalent to if you look at this chart here, the blue line is basically H0, what we're going to think is going to happen under our specified null hypothesis. This is what we think is true. This is our null hypothesis. And then we have our specified alternative hypothesis, which is this red line. And you can basically see this dashed line here is basically our threshold. This is the value above which we would reject the null hypothesis. Basically above, this is our critical z-statistic, if you want to think about it that way. If you're thinking about these just being from the standard normal, the z-statistic here. And you can see here that the blue area is our alpha. So there's a little bit of the H0 that's above the critical value. So that would be 0.05, for example, here. And then on this right hand, you can see that most of the alternative is still in the rejection zone. That's good. So we have a reasonable amount of power here. We're not, it's probably like 60% power or something like that. But if we were to increase alpha, that's basically equivalent to like shifting this critical value a bit further to the left, basically. So we're basically kind of getting a bit more liberal. And obviously, if we get it more conservative, it would do the opposite. It would basically shift it more to the right, and we'd have less power and a lower alpha. And you can see here that basically by shifting this to a little bit to the left, so that's like say, moving from 0.05 to 0.1 alpha, we now have more power, of course, because we have a easier chance of rejecting the null hypothesis. We haven't changed what the underlying assumed null and alternative are. We also have a higher chance of rejecting the null when we shouldn't. Basically, this type 1 error, this alpha error. And like that's one thing I often see in presentations at conferences and stuff is that people will say, well, the alpha is slightly inflated, but the power is also higher. And it's like, yes, that could be technically sometimes due to a legitimate insight there, but oftentimes that's just logically going to happen, right? Like if alpha is higher, power will usually be higher because the threshold, if it just becomes more liberal, then it's going to make both those things more likely, effectively. So something to keep in mind there when you talk to presentations, people, like, you'll often just see, oh, alpha is slightly inflated, but also power is higher, so it's not that bad. But it's like those two things are kind of very logically likely to happen together, so just something to keep an eye on. But obviously then the effect size. So if we just imagine, let's just assume the actual variance here, the standard error is the same. The increasing the effect size is effectively equivalent to taking this alternative hypothesis and shifting it to the right, right? So this red line here has now moved further to the right alongside the number line. So there's the statistic scale here. And basically you can see here that obviously because it's moved further to the right, more of the alternative is to the right of the critical z statistic. So more of the H1 is in the rejection zone where it wants to be. And so our power, our 1 minus beta, is higher. And so that's good. But of course, as I said, increasing the effect size, basically saying, I've just arbitrarily decided I think the actual effect size is going to be higher than I expected. That's something that could be true, but it's not something that you should be basing your sample size calculation on, right? Like you can't just arbitrarily say, actually, I think the effect size is twice what I expected previously. That doesn't really make a lot of sense. You have an estimated effect size, or you have some kind of clinically meaningful effect size in mind. That's what you should be bringing to these power planning. And then finally, sample size, the one that we actually usually do, is basically, and this is obviously similar to if we decrease the variance, for example, if we assume the variance was lower than expected. But basically, you can see that as the sample size increases, the standard error is getting lower. So we have less variation in our estimate. And you can see here that because this estimate, basically because the mean is above this, you can see the mean, the peak here. As this gets thinner and thinner, it's going to have more and more. It's going to have more and more of its probability on the right side of this. So it's going to become more specific, and you're going to have a higher power because of that. So basically, we're going to have a higher estimate. And because we know the alternative hypothesis is true for the purposes of power calculations, well, if this value is greater than 0, if it's in the rejection area, like even if it was just 0.1 above the rejection area, if we increase n to infinity, we will have a 100% chance, because this will basically become a line, like a single line almost within the probability mass, that will be above the critical threshold, and you would have 100% power. So basically, sample size is kind of moving asymptotically towards that point there. But basically, there's a kind of compromise zone where sample size is being increased enough that this amount in the rejection area is sufficiently high. It's 80%, 90%, something like that. And so we're happy enough to kind of stop there rather than increasing sample size up to infinity. I will mention, and this is kind of a summary of the previous webinar I mentioned, the kind of everything you need to know about sample size. There's lots of guidance you'll see, like lot ChatGPT generated fields a lot of time, like how to increase your power. And there are increase your effect size, make a one-sided test, a two-sided test. Like these are things you can do in theory, but they're not really things you should have control of, or things that you should be arbitrarily doing. So I provide here are kind of what I consider to be more actual practical choices you could make at the planning stage that will increase your power. The big one, and one I think you should definitely do, avoid simplifying your data. So if you have continuous data, don't turn it into binary data. Don't dichotomize it. If you have count data, don't turn it into survival data. Don't turn it into binary data again, or categorical data. Keep it as count data, and things like that. If you have survival data, don't turn it into binary data or categorical data. And basically, you have this really bad trend, talked about Sen 20 years ago now, of dichotomania. One example of which is called responder analysis, where you have a continuous outcome and you just decide to arbitrarily cut it in half, and you can very easily show that will reduce your efficiency by at least a third, but often much higher. That's the best case if you split by the median effectively. So analyze your data. If you analyze your data as is, unless you have a very strong justification, like a medical justification for not analyzing data as is, for turning continuous data into categorical data, you can massively increase your power compared to in the case where you did that responder analysis, that dichotomization. So as I said, you could easily increase the sample size by 50% by just making that one choice to turn continuous data into binary data. If you have additional data, one easy way you can do that is covariate analysis. The covariate analysis is very widely understood. There's FDA guidance saying, you should probably do included covariates. And these are what I would consider usually be pre-specified covariates, things like age or gender, or some kind of maybe some kind of biomarker or something like that. So these can be included in your model. So in the simplest case, an ANCOVA analysis, or a covariate within your regression model, like logistic regression model, stuff like that. And these will generally increase your power. Now, for sample size justification, it's often encouraged to kind of use the worst case scenario where your variable either isn't in the model or has no explanatory effect on the outcome of interest for kind of a baseline sample size calculation. But regardless of that, your power, your chance of succeeding, given that some of your effect size that you're assuming to be true actually is true, will be higher if you include your covariates, and those could then be used as justification, say if you're in less rigorous like preclinical research, stuff like that, to maybe move things a little bit around, as long as you can justify that your explanatory variable, whether that be age or biomarker, actually will have decent explanatory effects. You can then include those. And of course, if you get into a more complex approach like Bayesian borrowing, you can use historical data, real world data, also that should increase power on average as well. And then, yeah, you should also consider study design. So, you might be avoiding study designs, but these study designs could be great ways to, reduce your overall expected sample size. So like group central design, very commonly is adaptive design, very well understood. And like Jennison shows that with a very standard group central design, with only a few interim looks, you could have 30% less expected sample size under the alternative hypothesis, and I think under the null similar, while only increasing your maximum sample size in the worst case scenario by about 5%. So the trade-off there would usually indicate that you have a good chance that is a worthwhile trade-off. Other adaptive designs like platform trials can allow you to have like multiple arms compared to the main arm at the same time. These are also called umbrella trials, context of oncology, and these could all, by having a shared control, and you can then reduce the overall sample size significantly and increase your power by extension. Paired or crossover designs, if they're allowable in the context that you are, like obviously there's certain assumptions for these type of analysis that may not make them applicable to your scenario, but if they are applicable, crossover designs can be way more efficient than an equivalent parallel trial. You're basically getting all this within subject information that you're not getting for the parallel trial that can then be used to increase your power. Basically, you're getting rid of some of the unexplained variance if you're talking about like the means ANOVA type case. And like factorial designs, if you have lots of comparisons or complex comparisons, factorial designs is something that lots of statisticians suggest that you should investigate. Now, obviously, all those kind of depend on ensuring that your sponsor, that the regulator, whoever other stakeholders involved are open to this, but these are strategies that could help you increase your power that aren't just arbitrary saying, hey, increase alpha or use a one-sided test. Those are kind of, I would consider to be arbitrary choices, or ones that don't often have a strong justification. These are ones which I think you can easily take in as feedback and take into your analysis and see, are these options that would make sense for my trial, that would increase my power. So then we get into calculating power. And so, given that calculating power is an important thing, there's a correspondingly large amount of books, papers, software that are provided for calculating power for a variety of statistical designs, statistical models, different hypothesis tests, and many, many more scenarios. And even if we get into like Bayesian approaches and complex approaches, very many often then will calculate the power as a byproduct under a specified alternative regardless. And so there's widely used books and primers. Many of them are provided in the references sections of the slide deck. Obviously, you can go to statsols.com if you want to know more about Encri, which is one of many software out there for calculating power, for calculating sample size. I'm not going to advertise the opposition in the webinar directly, but there are lots of other options out there, ranging from free to very very complex and deep commercial offerings as well. But I think in terms of calculating power, what are our three main approaches? There's basically approximate, often also referred to as analytical, exact approaches, and simulation-based approaches. And it's common for any given scenario, so that being the design, test, hypothesis, that there might be multiple examples, multiple different versions of the power calculations, but within each of these categories, so multiple different approximations, but across the different scenarios. So here's someone who used an approximate formula, here's someone who used an exact formula, and here's someone who used a simulation-based approach to calculate the power for that particular scenario. And basically choosing the best approach for your trial is often a function of your available resources, which includes your expertise. And what I would often say is that even for more sophisticated organizations, so large pharmaceutical companies, what you'll often find is they might start with an approximate or exact formula, which are a bit more restrictive than simulation, and then use that as a jumping off point, basically as a sanity check, to then go into kind of the more complex assumptions they want to explore for the purposes of power calculations and other success criteria that are of interest, such as evaluating type 1 error. So it's often true that multiple different versions are used by the same statistician or by the same researcher to kind of get a broader view of what they need to worry about in the context of planning their study, doing their sample size calculations, comparing different methods to see which has the best power. So approximate power, this calculates the power function using approximate methods and formula. Often these are rearranged for sample size, like we did earlier, if you're interested in that. There's this one paper that kind of talks about skew distributions, is included in the references, and it actually shows like you could apply this normal approximation approach, which is the most common, to basically nearly any scenario you could think of. So it does it for negative binomial, Poisson, binomial logistic regression, for gamma regression. So this is a very flexible approach. And if you want the kind of the Rosetta Stone of a very large amount of the approximate approaches, there are more sophisticated approximate approaches, to be clear, but most of them, if they're based on normal approximation, basically look like some version of this, where you have your critical z statistics, so that's like 1.96 for 0.625 alpha one-sided, z beta, so for 80% power to be like 0.84. So that's just once again running your kind of your Q norm, your kind of ZTF of the normal distribution to get these statistics. And then you have your V0 and V1. And this is basically the variance calculated under the null hypothesis and the variance calculated on the alternative hypothesis. And just one thing to note is that most of the complication in these approximate derivations is usually in calculating V1. V0 is usually fairly well defined because it's kind of required to do the hypothesis test in the first place in many cases. But V1, defining that under the alternative, but mostly talking here about superiority hypothesis, where if we assume the ratio is 1 or the mean difference is 0, it makes V0 much easier to calculate. But under V1, it can be a bit more intense. So there's a lot more derivation required to get to a point where V1 has a reasonable estimator. And so basically you have these Z statistics, these variants, and that most of the papers you read basically are about calculating these variances. And then you have your link by your effect size. So your effect size could be your risk ratio, it could be your proportion difference, your mean difference, it could be your hazard ratio, your log hazard ratio, it could be your log rate ratio, whatever happens to be. And link here just refers to the fact this could be the log, the square root, or some transformation of the original scale, rather than just using putting in hazard ratio directly into the denominator here. And that often gives you much superior performance. So you're much better using the log hazard ratio than the hazard difference, effectively, or the hazard ratio, typically in most, say, log rank calculations. And so you can see here, like it said Rosetta Stone, the t-test, and we kind of covered this is the approximate t-test calculation. Basically, it's also the exact calculation for the z-test, just to be clear. But this is the approximate t-test calculation. And you can see here, okay, log rank test, the Schoenfeld approximation for the number of events here, to be clear, rather than the sample size. But you can see here, it's like 4. You can see alpha, you can see the z alpha and the z beta are there. You see log hazard ratio, so that's our link delta. And you might be wondering, where is the variances? And basically, you can show that the variances in this case are just proportional to 1 over e, and so they basically get consumed into this e term over here. And this is just to be clear for the equal sample size per group case. For this case, actually under the null hypothesis assumption as well. So this approximation comes out. For the 2-sample chi-squared test, based on the Fleiss approximation, there's actually a whole bunch of different approximations, but the Fleiss one is probably the most common. You can see here, this looks pretty much the same as above. We have our proportion difference, so we're not doing any link function here. We're just using the identity link. We're just using the proportion difference as is. But you can see here, we have alpha hat, basically our mean proportion. So if it's equal sample size, it's like pi 1 plus pi 2 divided by 2. Obviously use the weighted mean if you have unequal sample size per group. We can see here under the null hypothesis, we're assuming, okay, under null hypothesis they're both equal. But are they both equal to pi 1 or are they both equal to pi 2? Well, let's just do a compromise where they're both equal to the mean of pi 1 and pi 2, effectively. And then under the alternative, where they're actually different, let's use the unpooled variance, where obviously now, actually, this is what's happening under pi 1 and pi 2. That's what we actually defined under the alternative hypothesis for power calculation. So that's what goes into the V1 slot. So that kind of matches quite well to like how these, and that's a very easy example. And then you can see for Poisson, very similar to the Schoenfeld for this very simple approximation, which I believe is for the 1.96 case. That's why this is 4 instead of with the z alpha, z beta. But you can actually easily turn this into the z alpha, z beta if you want. Basically, just happens to be that for 80% power and 5% significance of two-sided, this turns out to be 4, this term here. And you can basically see here that we then have our square root difference between the square roots. So obviously we know square root transformation quite used often for the Poisson. And so this layer approximation is a very simple approximation for the Poisson case. And so that's kind of this Rosetta Stone kind of creates all of these approximations. As I said, there are more complex approximations. So for example, for the log rank test, you would have the Lakatos approach, which is like a Markov process, but it's still an approximation, right? And these are basically used because they're usually easier to derive than the exact calculations. It's very often quite difficult, if not potentially impossible, to derive the distribution under the specified alternative. And so there might not just be an exact solution, or might require some very restrictive assumptions to get to that exact calculation, quote unquote. And also they often tend to be, much easier to run. Like, this is a very trivial formula. This will run in seconds if you write this up in OR or SAS or similar. That's less of a consideration now, obviously, with modern computing and such, but it is something that can still be of interest. And certainly when you get to exact calculations with high sample sizes, there can still be a limit there. And I would say that these approximations will often have a simpler set of inputs than, for example, simulation-based approaches, but that does mean they basically often are using hidden assumptions. So, for example, if you're using a repeated measures method, they'll often be assuming a compound symmetry covariance structure, which may or may not be true for your particular situation if you're talking about, say, repeated measures, mixed models type scenario. And so, be careful, be aware of the hidden assumptions, read the original papers, read the reference material from software such as from Inquiry, and kind of make sure you understand what you're doing. But for most cases, this is a useful benchmark, a useful starting point for getting your power. And, then you could kind of go, okay, let me just check, does the exact calculation give the same result? Good, round correctly? Great, that's good. But especially if you're going to simulation-based approaches, you now have a benchmark. Can you first verify that you can calculate what this approximate equation is supposed to go, the specific scenario, and then kind of bounce off into including dropout or more complex covariance structures and things like that. And as I said, simulation is usually included as part in most papers these days as part of the benchmarking of these approximate formula. You basically see a big table saying here's what the sample size was according to the formula across all these scenarios, and then there'll be a column saying simulated power was around equal to what it's supposed to be typically. If we move on to exact power, this is kind of in the same, I would say, branch as analytic power. It's basically just like the more exact approaches. And basically exact power calculations are basically saying, okay, we don't want to just approximate the power function. We actually want to understand specifically what the power function is. So we can derive, a formula or a methodology which will calculate the exact power function. So given the specific alternative, we can calculate all of the parameters that would go into the statistical test, get out the p-value or the critical statistic, or sorry, the actual statistic, and compare that to the critical value, and we can get out what the probability of that occurring is, effectively what the power function is for that specific alternative is. So, it's important to note that this shouldn't be confused with exact tests, which is often a language used very commonly in the context of binary data, categorical data, sometimes count data. Exact tests are ones which guarantee type 1 error control, either conditionally or unconditionally, basically conditioning on the margins of the table. If you're thinking about, say, a 2x2 table, conditioning on the control proportion, and unconditional, basically you're not conditioning on that. You're basically allowing that to be free and finding the threshold for the worst case scenario for that variable used to be fixed, that margin, for example. So don't confuse these. You can have approximate power for exact tests. You can have the approximate power for, say, the Fisher's exact test, but you can also have exact power for approximate tests. So you have an approximate test and you want to have the exact power, assuming you're going to use an approximate test, so you're going to use the chi-square test, you can get the exact power that will have for the given scenario. So just don't conflate those two things. Derivations are available for many scenarios, but sometimes they're often quite complex and much more difficult to implement than the equivalent approximate method that might be more widely used. As I said, the variance is often the parameter that's of most complexity in terms of deriving under the alternative hypothesis. And there's sometimes trade-offs in terms of performance, legibility, sometimes there's just tradition in terms of these calculations are the kind of standard ones that we usually compare against. So even if exact methods are available, oftentimes they're not used. So for example, I'm aware that there's exact t-distribution based sequential tests, but the vast majority of sequential tests will use the normal approximation work even for the continuous case. So for example, there's the GSE-T GSET OR package. I think it's now been pulled at this point, but that provided the group sequential design for equivalence testing using the exact bivariate t-distribution, but most people just still use the kind of normal approximation for that case. So there's still many cases where the approximation is used even if exact methods are available. They're often computationally expensive, especially for discrete data. So you're thinking about count data, you're thinking about binary or categorical data. Basically, this is because you basically have to, for categorical or discrete variables, you have to enumerate all the scenarios effectively. And sometimes it's easy, sometimes it's not so easy. So if you think about this two sample proportions case, you have to compute the t-statistic and p-value for the desired test for every single scenario for from 0 to n1 and 0 to n2 for this kind of two sample proportion test, so like a chi-square test or a z-test, or it's like a Fisher test. And just to note here, the exact test for the chi-square test and the exact test for the Fisher test are done the same way, even though the Fisher is an exact test and chi-square is a not approximate test, but the exact power for each is kind of enumerated the same way. So, you have 0 to n1, 0 to n2. So you imagine here, that's like 0 to 100 in each group. That's 0, 0, 0, 1, but it's also 1, 0, right? And it's also 1, 1, and 2, 1, and 1, 2. So you're taking all of those different scenarios, basically the product of each plus 1. So n1 plus 1 times n2 plus 1, and just multiply those together. That's all the scenarios. You have to enumerate all these. And, for these days, you could do up to thousands, but if you get into like, tens of thousands, that's not really going to scale correct. And basically what you have to do is that for each of those scenarios, calculate the critical test statistic or the p-value, the ones that are significant, so the critical value is above the critical threshold, or where the p-value is significant, put those in the rejection set, and then basically sum the product, basically how likely each of those scenarios are under the specified pi1, pi2, under your actual true assumed alternative group 1 and group 2 proportions. And you can see that here, that's basically just, the binomial distribution. So this would be d-binom, basically, if you're using OR code. But you're doing this for the entire rejection set. Now, there are ways you can cut out unlikely scenarios and stuff like that to make this less onerous, but still, if you're doing this the full way, it can become quite computationally expensive, and it'll take a while to run, even in software such as nCree, which does some of those optimizations. But you can see that for certain cases, like say the two sample t-test, like the derivation for this isn't trivial because you're using the non-central t-distribution here for the derivation rather than the z-distribution, but it's not too difficult, right? It's just you basically calculate the critical t-statistic using the t-distribution instead of the normal distribution with degrees of freedom equal to 2n minus 2. Obviously here again, assuming sample is equal per group, and that's the sample size per group. And then, with our critical alpha, 0.025 or 0.975, you're using 1 minus alpha. And then our NCP is just basically our effect size that we talked about there, our standardized effect size times square root of n. And as you run this through a non-central t-distribution with the critical test statistic, the degrees of freedom, and then our NCP, and that will give us that power. So it's not that complicated. It's very easy to do with modern computing, but back in the day, this would have been considered to be a bit more difficult to use the non-central stuff. And even now, some of the approximations used for non-central t-distribution can be a bit wonky. Even the one in OR, I think, has some issues compared against other packages that are a bit more robust. So, exact power calculations, they are still limited to your underlying distributional assumptions. So for the two sample t-test, we're basically are for this derivation assuming our data is coming from two normally distributed groups which are independent, and IAD sampling and all that kind of stuff, and proportions is still making all the assumptions required there. But you may want to then consider simulation if you want to, like the exact calculation might be available for a very specific scenario, but maybe there's other scenarios which aren't covered by the exact calculation that you might want to evaluate the kind of empirical power under those. So simulation is probably the most flexible, but also by exchange is also the most flexible, most complex, right? Because you're having to specify, you have a huge amount of control over basically everything. So basically in simulation, what we're basically going to do is we're going to specify what we're going to think is going to happen under the alternative, basically, all of the things. We're going to basically feed, we're going to simulate data under that specified alternative. So simulate what actually is going to happen, simulate actual subjects or from the distribution we think is going to be true under the alternative, and then we're going to run directly through our statistical procedure, get a significant p-value or not, and then count how many significant p-values are, or how many successes we have, and the number of successes divided by the number of simulations is empirically our power. It's our simulated power. And this is really flexible. It handles complex scenarios, extensions. As we get into more complex derivative designs, adaptive designs, Bayesian designs, simulation is becoming the default approach for verifying both the type 1 error of your design, but also for doing power calculations as well. So, it requires a bit more computation. It requires a bit more expertise. Like, this is probably not something you would want to do if you don't have some statistical assistance. Though there are now increasingly more tools that can make this a bit more easy for non-statisticians to kind of use for certain sub areas or certain sub scenarios. And basically, you have all of this control over the data generating process. So you fully control that, and then you just have to run that through your procedure, which you have full control over again, and then you get your p-values out, and you basically see how many are successful compared to the number of simulations, and that's your power. That's a huge amount of control, but of course, all that control means that, you know, now you have all these other things you could change, all these other things you could consider. And obviously for each of these things, you have to make assumptions. You're still making assumptions. So if you want to, you know, simulate from a complex mixture normal, you now have to define what the normal distributions that went into that mixture normal are, not just a single mean and standard deviations. You have to define, you know, 2 or 3 means, 2 or 3 standard deviations. So, you know, the more complexity you have, the more assumptions you have to do. And if you're talking about power in the context of planning pre-trial, the more assumptions you have, or the more things you're basically making guesses around. So, you know, to a certain extent, you know, that could then multiply at effect. And I would say that, you know, there are cases where simulation is much better than the approximate approach, you know, for more complex scenarios. But it's also true that the more assumptions you make, the more you are basically choosing to go on your own path that's further from the kind of standard assumptions for that particular scenario. So you need to be comfortable that you're willing to reject, you know, the covariance matrix should be CS or A or 1, and you want to use an unstructured one. Like, you should really understand what you're doing when you're making that choice and how much of an effect that might have on power before making that. But as I say, even if you're going to do simulation, it's often still very useful to kind of start with an exact calculation or an approximate calculation as a sanity check. Kind of just first verify, can I replicate the power from that approximate formula under its fairly standard assumptions, its hidden assumptions, or whatever, however you want to call those, and then kind of iterate out of that, kind of iterate and kind of move into more different scenarios based on that. So, you know, if you want to talk about, you know, simulating, you know, for a t-test, for example, you would basically simulate, you know, from say 2 normal distributions, you know, n1, say 100 mean, like mean value, like 100 values with mean 1 and standard variance here, and then 100 from the mean 2, and then basically you calculate the t-statistic or the p-value. You compare them against the critical threshold. So it's a t-statistic greater than the critical t-statistic, is the p-value less than the test significance level, and if it's significant, add it to the success counter. Repeat this 1,000 times, say 1,000 simulations, and then the power, as I said, is the number of successes divided by the number of simulations. So that's kind of a brief overview of what a simulation strategy would look like. And they're often given in this kind of LaTeX type format here. This is kind of generic, like high level one, but you'll see things that look like this when you talk about specific simulation as described in papers that use this approach. So I think we're basically out of time, so I apologize for that. But statistical power is the probability of finding for success given a specified alternative hypothesis scenario. Or if you want to take more high level, step 0, you know, as long as we're willing to define a success criterion, it's basically how likely are we to have success given a specific scenario, alternative scenario, is passed through into our statistical procedure. So that's the kind of highest level idea of what power is. And power is very useful for study planning. It can be used to compare different designs. It'll be used to find the appropriate sample size for your study and other beyond. The 3 primary ways of calculating power are approximate or analytic approaches, exact calculations, and simulation-based power. Each has its own strengths and weaknesses in terms of complexity, in terms of numeric requirements, expertise requirements, but approximate formula, I would say, are often a useful starting point, while simulation is what you want if you want to really get into the weeds, if you want to do something more complex, or you want to start playing around with some of the more complex scenarios that occur. So, you know, for example, if you wanted to move beyond just normal distributions, which is kind of the assumption used for our approximate formula, and kind of say, okay, now we want to assume they're both from exponential distributions, you know, the simulation is a much easier way to do that than, you know, there are approaches for doing that for using approximations, but it might make more sense to do that via simulation than using those approximations. So just with the final couple of moments here, I'm sorry I won't be able to get any questions here, but I will answer those via email. So continue to put those in and I'll answer them afterwards before we finish up. But if you don't have nQuery or you don't have a current license of nQuery that includes, say, the Pro tier, you can try all of the features of nQuery for free for 14 days online at statsals.com/nQuery-demo, and no credit card or anything required. We just need an email to send you a link, and you can try nQuery within your browser for 14 days and see if there's features there or things that you're interested in knowing more about. And finally, I just want to thank you so much for attending today. If you want to get in contact with me or later on, you can email info@statsals.com. As mentioned, statsals.com is a website. You'll find all of our previous webinars alongside other resources that have been created by our team, and also information on pricing and the tiers and other information. As I mentioned, there are references at the end of this webinar, including the previous webinars I alluded to during this webinar, books if you want to know more about power or sample size, trial design overviews, hypothesis testing perspectives, alternatives to power and sample size, and the views on that. There's some Shiny apps here that have been very useful for understanding this area further, post hoc power and why not to use it, the prevalence of underpowered research and practice, Strategies to improve your power, those things I talked about, like dichotomania, avoiding that, ANCOVA, adaptive designs, crossover designs, categorical, and then some for each of these categories of approximate, exact, and simulation power. There's some overviews and also some specific papers that cover those for specific scenarios for the exact and approximate scenarios as well. That paper I referenced with the gamma distribution, for example, is this Kundal paper here from 2015, for example, if you wanted to look into that further. So as I said, we've run a little bit over time, so I won't have time to go through questions, but I do want to thank you one more time so much for attending today. I hope there was some useful information here that will be useful in your practice. And yeah, we'll have our next webinar next month. I believe that will probably be on vaccine sample size, so look forward to that. And yeah, once again, thank you so much. Hope you have a great day and talk to you soon.